Okay, let me go to the PowerPoint. Okay, so as I recall, the last thing we talked about were the different types of integrated rate laws, which relates the concentration of a reactant to time for different types of reactions. We did the zero order, first order, and second order reactions. And basically, of course, I won't recap everything that we did last time, but basically it comes down to these equations right here, all right? So we determine what the concentration or what the relationship between concentration and time is for zero, first, and second order. And we also determine the half-life equations for each type of reaction. And I just remembered I should have shared my screen as well. So let me do that now. Okay. Okay, so you guys out there should be able to see my screen now. So basically, this is what we ended with. Come on. Okay, so let me bring this back up on the screen. So this is basically what we covered the last time, all right? And as I recall, we did some assignments. Did we? Hold on, let me see here, just to refresh my memory. What assignment did we cover? In assignment number 2, let's see here. Can anybody remind me? Did we go up to question number? Did we do question number 6? I don't remember if we did question. I think no, we did 5, right? Okay, all right. So let me quickly go through question number 6. And in question number 6, it says the differential rate law for the reaction of iodine atoms to molecule iodine, and it gives you the equation is given. Rate is equal to K times the concentration of I squared, where K is equal to 7.0 times 10 to the 9, all right? So the question is, what are the proper units of K? So how would you answer that question? Anybody? Let me write down what you're going to need in order to answer that question. Basically, you're going to need this equation right here, right? And what the question is asking for is the units of K. Now, my question to you is, what would be the units of concentration squared? Anybody? What would you expect the units of concentration squared to be? M squared. Okay, so this would be M squared. And what would you expect the units of rate to be? M over S, or M over any unit of time, right? The question didn't specify the time unit, so it could be seconds, it could be hours, it all depends on the reaction, right? So if that is true, then how would you expect to determine the units of K? If rate has this unit and I squared has M squared as the units, then how would you determine the units of K? Right, because you know that K is equal to rate divided by the concentration of I squared, right? So correspondingly, you would divide the rate unit, which is M over S, by M squared, right? Excuse me. So therefore, the result of that is that the M here will cancel out one of the M of the M squared. So the final units would be M to the minus 1, S to the minus 1. So that would be the unit of K for this reaction, all right? Okay, now the B part says, if the concentration of I initial is 0.40, and the time is 2.5 times 10 to the minus 7 seconds, then you have to calculate I. Now, in other words, we have to use, well, okay, so how would you solve this problem? And let me give you a hint. The hint is the reaction is second order. So there's an equation that we learned which relates the concentration to time for a second order reaction. What would that equation be? You can look in your notes, feel free. What's the integrated rate law for the second order reaction? Okay. Okay. Plus KT, very good. So that would be the equation you're going to use. What the question is asking for is this right here, right? So let's plug in the numbers. 1 over 0.40 m plus K. What is K? K is equal to this right here, which is 7.0 times 10 to the 9. And here is where we figured out the units for K, which would be m to the minus 1, s to the minus 1, multiplied by the time, which is 2.5 times 10 to the minus 7 seconds, all right? And that will give you 1 over I. And I did this calculation already, and I got 1800 m to the minus 1, and that is equal to 1 over the concentration of I, which means that concentration of I would be equal to what? Over 1800 m to the minus 1. And when I did that calculation, I got 5.6 times 10 to the minus 4 m. And that's how the B part is done. All right? Any questions about this? Any questions? Any questions? Any questions? Okay, so is it okay for me to clear this? Okay. So let me clear all this. Let me do this, and let me scroll down to question number C. Now, question number C is asking for the half-life if the initial concentration of I is 0.40 m. Okay, so what equation would you use to solve for T half? What is the equation? In other words, what's the equation for the half-life for a second order reaction? T half is equal to what? 1 over concentration of I initial. This is looking messy. All right, so that's 1 over K. What was K again? 7.09? I'm sorry, 7.0 times 10 to the 9, my bad. And this would be m to the minus 1, s to the minus 1, times the initial concentration of I, which is given as 0.40 m. And when I did that calculation, I got, and folks, please confirm these because I could be wrong. I would strongly recommend that you confirm these calculations. But that's what I got. 3.6 times 10 to the minus 10. All right. Any questions about these? Any question about this one? Any question about this one? All right, is it okay for me to clear this? All right, so let me do so and move on to D. Now, D says, if the initial concentration of I is 0.80 m, how much time would it take for 75% of the iodine atoms to react? Okay, so what equation comes to mind for this question? What's the equation relating the concentration to time for a second order reaction? I think we met it before, earlier. I think in part, which part? Was it part B?
Yeah.
Yes, part B. So what's the equation? 1 over the concentration of I is equal to what? 1 over the initial concentration of I plus KT. All right. Now, what the question is asking for is T, right? How much time will it take for 75% of the atoms, the iodine atoms to react, right? So we can rearrange this algebraically. And if you do that, you're going to get T is equal to 1 over K multiplied by 1 over concentration of I minus 1 over the initial concentration of I. All right? So it's a question now of plugging in the values, right? Now, we know what K is because that was given originally in the question. We know what the initial concentration of I is. The only thing that we don't know directly is what the concentration of I is. But you're told that 75% of the iodine atoms will react. So how does that help us to determine what the concentration of I would be at that time? They said, the question says that 75% of all the iodine atoms reacted at this time, right? So how does that help us to determine the concentration of I at that time? I'm sorry, multiply. Not quite, because look at how the question is worded. How much time it would take for 75% of the iodine atoms to react? This I here represents not the amount that reacted, but the amount that remained. You see what I'm saying? The concentration of I in the question here is not talking about how much has reacted. It's how much has remained, I'm sorry. So if 75% of it has reacted, what does that mean? 25% will remain, right? So basically we can say based on that, that the concentration of I is equal to 0.25 times the initial concentration of I, right? Or in other words, 0.25 times 0.800. And according to my calculation, that will be equal to 0.20 m, all right? So now that we have the concentration of I, we can calculate for T, which is 1 over, what was K again? 7.9, 7.09, 7.0 times 10 to the 9. I keep screwing up with that. And the units here would be m to the minus 1, s to the minus 1, times 1 over 0.20 m minus 1 over 0.80 m. And that's it. Do the number crunching, and according to my calculations, 5.4 times 10 to the minus 10 seconds would be the answer. All right. Everybody see that? Any questions about that one? Any questions? Okay, so let us clear this and go to the PowerPoint and move on to the next topic. I'm going to try to finish this chapter today. So, let me get out of this here. All right, so let's talk about some energy changes that takes place in a reaction and how it relates to kinetics. All right, so what we're looking at here are what we call energy diagrams. You may or should have met this before in General Chemistry 1, thermochemistry. What this shows you basically is how the energy change for a reaction as you go from reactants to products. So this is purely hypothetical. We have the reactants AB and the products are CD, right? And they're showing you basically the diagrams for both an exothermic and an endothermic reaction. So AB here is reacting to form CD, and you'll notice that the energy of the products is lower compared to the energy of the reactants. So that is what typically happens in an exothermic reaction, and the reverse is true for an endothermic reaction. Now you'll notice that as you start from AB, the energy increases, right? So basically what this means is that the reactants are absorbing energy from its environment until you get to a maximum peak here, where you have a temporary, very fleeting combination of AB existing, right? The result of coming together of the two reactants. And then after that, the energy falls off and then you get your products. Whoops, sorry. So, okay. Now this energy here that I just talked about, where you have this transient species here, which has a higher energy compared to AB, that energy difference is called the activation energy of the reaction, right? And by definition, the activation energy is the minimum amount of energy required for the reaction to take place, right? What this means is that if the reactive molecules, if the molecules on the reactant side, if they don't have at least the activation energy, then the reaction will not take place, right? And what that means, basically, if you could actually see the molecules, is that the molecules will collide, but they will bounce off each other without changing, right? That's basically how we interpret the whole role of activation energy in a reaction, all right? Now, I kind of alluded to the collision theory by what I just said. The collision theory basically states that basically in order for reactant molecules and atoms to react, they must collide with each other. And if the reaction is to take place, the collision would have to be such that it's effective, which means that the reactive molecules, as I said before, must have enough energy to cause bond breaking, all right? And this diagram here basically demonstrates the difference between the same reaction at two temperature levels, because one of the things that affect the rate of reaction is temperature, right? So this could well represent the reaction that we just looked at a while ago. Just to explain what's happening here, the y-axis basically is where you're going to plot fraction of molecules having a certain amount of kinetic energy, and the x-axis is basically kinetic energy, right? And in the case of the lower temperature T1, this is the curve for that, the blue line, and the red line here is the curve for the higher temperature T2, right? Now, let's say that the activation energy for this reaction is represented by the point right here. So, okay, right here, let's say that represents the activation energy, all right? Then basically at the lower temperature, what you'll find to determine the number of molecules that would have at least this energy here, you'd have to find the area under the particular plot. In the case of the lower temperature, this would be the area right here, the shaded line right here. And therefore, that represents the number of molecules that have at least the activation energy at temperature T1. At a higher temperature, the number of molecules that would have that energy, as you can see here, is under the area here where the pink line is. So therefore, what this tells us is that as the temperature increases, more molecules will have at least the activation energy, and therefore the reaction rate will be faster. And there's actually an equation that establishes the relationship between the rate constant of the reaction and the activation energy. So that's basically what the collision theory is all about. It explains the role of activation energy, which is the minimum energy that is needed for the reaction to occur. Another important factor, which influences the rate of reaction, or the possibility of the reaction, is the correct orientation of the molecules as they are reacting. And one example here, which is one that you'll meet if you have to do organic chemistry, is a reaction between these two compounds, methyl bromide and iodide ion. So the actual equation for the reaction is CH3Br plus I minus to give CH3I plus Br minus, right? So this is the overall equation, right? And this is the shape of the methyl bromide molecule, and this is the iodide ion. And we're looking at two possibilities where the iodide is approaching the molecule from where the bromine is, and then you have this possibility where the iodide is approaching the carbon. The question is, which one of these collisions will be more successful? And we can actually predict which one will be more successful if we take into account the polarity of the carbon to bromine bond. So if you remember anything about polarity, polarity is a separation of charge within a bond or a molecule. In this case, we're focused on the bond. And since bromine is more electronegative than carbon, the bromine will have a partial negative charge, the carbon will have a partial plus charge, and the iodide ion, of course, will have a negative charge. So therefore, this collision here will not be as successful, or will not be successful at all in terms of carrying out the change. Because based on this equation I just wrote up here, the change involves the replacement of the bromine by the iodide. If you have the bromide, which is negatively charged, or the bromine, which is partially negative charge, and the iodide, which is negatively charged, you'd expect some repulsion. So therefore, this would not be a successful, not successful collision. All right. On the other hand, in this case here, because the carbon is positively charged, iodide is negatively charged, then this collision here would be successful because, of course, unlike charges, success, what do you express as E, S, full collision, all right? This collision will be successful because of the attraction between the iodide and the carbon. And as a result, this bond will break, and therefore the iodide will be bonded to the carbon, and the bromine will leave as a bromide. So basically, this is just one relatively simple example which demonstrates the importance of the orientation of the molecules with respect to each other as the collision is about to occur, right? Basically, what this is telling you is that not all collisions will be successful, right? The collisions will only be successful in some reactions if the orientation relative to each other of the molecules, atoms, ions, whatever, is lined up right, basically, all right? So that's a very important aspect of the collision theory that you have to take into account. So just to summarize, two important things that need to be necessary in order for the reaction to take place. One is that the reactive molecules must have at least a minimum energy in order to cause bond breaking, which would lead to the product formation. And then the second is the correct spatial orientations of the colliding molecules. That is also very important in order for you to have a successful collision, which leads to product formation. Okay, another important aspect of these types of reactions, and this goes back to the energy diagram representation showing the energy changes as the reaction progresses. And that has to do with the transition state theory. Basically, I kind of alluded to it earlier, where up here in the energy diagram, we have a species where it's very transient. That's why we call it a transition state, where you have bond breaking and bond making occurring simultaneously, all right? And to the best of my knowledge, nobody has ever isolated a transition state to figure out whether or not, what we expect it to be is the case. But we believe that, we can figure out what the transition state is based on the reacting molecules and the products that are formed. So in this particular case, we're looking at the reaction. Let me write down the equation of this reaction here. the reaction here is between carbon monoxide plus nitrogen dioxide to form carbon dioxide and nitrogen monoxide. Whoops. All right, so that's the overall equation, right? So this is the carbon monoxide here. This is the nitrogen dioxide here. And basically, based on the fact that we have the carbon to oxygen bond being formed here, which was not present here, we believe that there is a partial bond formation occurring between the carbon and oxygen, and simultaneously a bond breaking between the oxygen and nitrogen, because now we have in the product side only one oxygen bonded to nitrogen where we had two here. So therefore, we can basically surmise that the transition state, which occupies this position here in the energy diagram, is a structure where the oxygen that is being lost by the NO2 and transferred to the carbon dioxide is partially bonded to both the carbon and nitrogen. All right? So basically, as you go from here to the product, this bond becomes more firm, become more stabilized and established, and this bond becomes more broken until you get to the products where this bond is established and the oxygen to nitrogen bond is completely broken. All right? So that's basically the transition state. And this is just one example. And again, this is an important idea to understand it. Again, if you plan to do organic chemistry, very often what you'll find is that you can actually make certain predictions of certain reactions in terms of the possibility of product formation or what type of products will be formed based on the structure of the transition state. So just some terms I need to introduce to you here at this juncture. So the other alternative term for the transition state, we call it the activated complex, all right? And as I said before, it's existent, is transient. It basically forms or it forms very quickly and disappears just as quickly, all right? Nobody, as I said before, nobody, as far as I know, has isolated the transition state, but we're fairly confident that we can determine what it is based on the reactive molecules and the products that are formed. The activation energy, of course, as we said before, is a difference in energy between the reactants and that of the transition state. And of course, the enthalpy of the reaction is a difference between the enthalpy of the products and that of the reactants. Okay, so that's the transition state theory. Now, what we're going to look at is the relationship between temperature and the rate of reaction. And almost always, can't think of any exception, what you'll find is that as the temperature increases, the rate of the reaction is increasing. So what you're looking at here is a plot of rate constant versus temperature. And you can see the increase as the temperature increases, the rate constant increases. So a guy by the name of Arrhenius, which in general chemistry 1 you would have met before, he did a lot of discoveries that very important in chemistry. He was the one who, for example, came up with the notion that certain compounds, when dissolved in water, produces ions, and that's how we know that ions exist when it comes to ionic compounds and so on. Anyway, so in this case, he delved into kinetics and he examined the relationship between the rates of reaction and temperature, and this is what he came up with as the mathematical relationship between the rate constant and the temperature. K is equal to A times E to the minus EA over RT. Now, I'm going to, in fact, let me tell you what these terms are. I think I have the terms listed in a subsequent slide. Let me check something here. Okay, here it is. So this is basically giving you all the different terms. EA is the activation energy, which we met before. R is the molar gas constant. Now, please note that the value of R that you'll be using is this value right here. For our purposes, we can round off to 3 sig figs. 8.31 joules per mole Kelvin. You are probably more accustomed to R being equal to 0.08 to 1 liters atmospheres over mole Kelvin, which is the same thing as this, but you'll notice that the liters atmosphere units here in this value of R is replaced by joules, right? So in the case of this equation here, we're using this value here for R, 8.31 joules per mole Kelvin. T is the temperature in Kelvin, and A is a factor known as a frequency factor, which takes into account not only the collisions, but the fact that the collisions are such that the molecules are oriented correctly, as I described earlier, right? Now, one useful way of expressing this equation is this right here. And this will require, in order for you to understand how to get from here to here, you should recall some algebra that you met before, right? All you do is find the natural log of both sides and then do some other manipulation, and you end up with this equation right here. And it turns out that this equation is in the form of an equation of a straight line, where ln k would be plotted on the y-axis and 1 over t will be plotted on the x-axis, which means that minus EA over R would give you the slope, and ln A will give you the y-intercept. All right? So if you were to plot ln k versus 1 over t, this is what you're going to get, right? You're going to get a straight line plot with a negative slope, right? And as I said before, the slope would be equal to minus EA minus the activation energy over R. So if you were to do a plot of this and you want to find the activation energy of the reaction, then you multiply the slope by the molar gas constant, and that will give you the minus EA, and therefore you can determine what the actual activation energy is, all right? So that's basically the relationship between the temperature and the rate constant. And therefore, as the temperature increases, the rate constant increases, which means that the rate of the reaction itself would increase, because the rate constant is basically directly proportional to the rate of the reaction. Okay, so the Arrhenius equation, or the A constant, as I said before, is called the frequency factor. And as stated here, it's a product of the collision frequency and the probability factor that takes into account the effective collision resulting from the proper orientation of the molecules. The other part of the equation, the e to the minus e over RT, represents the fraction of the molecules that would collide successfully to form products. All right, so those are basically the two parts of that Arrhenius equation. Okay, so with that said, let's go back to the assignment, and let's look at question number 7. So it gives you this equation, and it says that the rate constant at 300 degrees Celsius is 5.7 times 10. Oh, before I go to that, one thing I want to say, which actually relates to this equation right here. Let me go back to this here. So if you want to find the activation energy of a reaction, it's best to do something like this. In other words, you carry out an experiment where you determine the rate constants at various temperatures, and you get several data points, right? I would say no less than 5 data points for accuracy's sake. And then you do your plot of ln k versus 1 over t, and you get your straight line, and then you do your slope, and then based on that, you can find the activation energy. That would be the most accurate way of determining the activation energy. Another way, which is not as accurate, is basically using 2 data points, right? And those two data points would occupy the ln k value here and 1 over t here. And this and ln a would be unknowns, and therefore you'd have to determine using what we call, or what used to be called back in the day, I don't know what they call it now, use a pair of simultaneous equations. I don't know what the alternative term that is used nowadays, but back in the dark ages when I was in high school, we use the term simultaneous equation, right? And that's in fact what we're going to do in the assignment question that we're about to embark on. So, as I was saying, the rate constant is at 300 degrees Celsius is 5.7 times 10 to the minus 1, m to the minus 1, s to the minus 1. And at 230 degrees Celsius, it is 2.7 times 10 to the minus 2, m to the minus 1, s to the minus 1. So the question is asking for you to calculate the activation energy. So basically, the equation that we're going to use, let me get my writing thing here. Okay, so the equation we're going to use is ln k is equal to minus EA over R times 1 over T plus ln A, right? Now, in this case, they gave you two values of K and two values of temperature, right? So basically what you're going to do is, since that's all they gave us, we could do a graph, but it would be meaningless because we have only two data points. So basically what we're going to do is derive an equation which takes into account all these values. So what I'm going to say is that this here is K1, this here is K2, and correspondingly, this here is T2, and this here, T1, I'm sorry, this here is T1, and this one here is T2. Another thing we need to do is convert the temperatures to Kelvin. So in the case of 300, you add 273 to that, that gives you 573 Kelvin. And if you add 273 to this, that gives you 503 Kelvin, all right? Okay, so basically, I'm going to put K1 here and T1 here, and then I'm going to write down another equation where I have ln K2 is equal to minus EA over R 1 over T2 plus ln A, all right? Okay, so what I'm going to do now is divide one equation by the other, and, or not divide, I'm sorry, subtract. So if I were to subtract the bottom one from the top one, then the result would be ln K1 minus ln K2 equal to minus EA over R 1 over T1 minus 1 over, what's wrong with me today? 1 over T2. And of course, this LNA will subtract that LNA, so therefore the result of that will be 0. Now this can be simplified to ln K1 over K2, right? You all should know this, right? ln A minus ln B is equal to ln A over ln B, right? I mean, ln A over B, right? So that's basically how that makes this a bit simpler. Okay, so remember now, the aim of this exercise is to determine this, the activation energy, right? So I'm going to continue up here to see if I can do that. So based on what I see here, I would say that minus EA, or let me not say minus EA, EA is equal to, how am I going to do this now? R ln K 1 over K2 divided by 1 over T1 minus 1 over T2, all right? Okay, so with that said, all we have to do from here is plug the numbers in. R is equal to 8.31 joules per mole Kelvin times ln K1. What's K1? K1 is 5.7 times 10 to the minus 1, m to the minus 1, s to the minus 1, over K2, which is equal to 2.7 times 10 to the minus 2, m to the minus 1, s to the minus 1. And then below, as the denominator, I'm going to put 1 over T1. What's T1? T1 is 573 Kelvin minus T2, 1 over T2, which is 503 Kelvin. And that's it. And then you do your number crunching. And according to my calculations, the answer works out to be 1.04 times 10 to the 5. And that would be joules per mole. And that's because the kelvins cancel out here and here, and these units cancel out here and here, so the only unit remaining would be joules per mole. All right? Okay, as I said before, this is not the most accurate way of doing it because you have only two data points, right? And as I'm quite sure you know from your previous math experience, when it comes to the possibility of getting more data points, the better, right? And then you can plot your graph and get a more accurate value for things like the activation energy. And let me just say also, even though the question did not ask for this, you can also find out what LNA is equal to, right? I won't go through it, but you can try it on your own. In fact, you can find out what A is. All you have to do is take the K1 value, which is the 5.7 times 10 to the minus 1, put that here, the activation energy that you would have determined from here, which we just did, times 1 over the temperature, T1, which is 573, plus LNA, and then solve for LNA, and then solve for A, and that would give you the frequency factor, right? So I'm just letting you know about that, just in case you're asked a question of that type. Okay, any questions about this particular question in the assignment? Any questions? Any questions? Okay, is it okay for me to clear? Oh, got to take a picture. Okay, can I clear now? All right. So let's go back to the PowerPoint. And keeps doing that. Okay, so now we're going to talk about a very important aspect of kinetics, reaction mechanisms. And let me just say that what I'm about to discuss not only applies directly to pure chemistry, but basically any system where you have chemical reactions taking place, including what type of reaction that takes place in our bodies. All right. So let's talk about reaction mechanism. Now, let me just say this. If you're given a chemical equation, right, the only thing or the only information that that chemical equation tells you are what you start off with, the reactants, and what the products are, right? It does not tell you anything about, as you go from reactants to products, the type of molecular or ionic changes that will occur, all right? That is what reaction mechanisms is all about. And a lot of elucidation of mechanisms involves kinetics, all right, as you're going to see. So as stated here, the overall reaction can be represented by a series of elementary reactions, all right? And basically that collection of elementary reactions in sequence, we call that the mechanism of the reaction. So just to give you a simple example, let's say you have a reaction between nitrogen monoxide and oxygen to form nitrogen dioxide, right? And let's say somebody was doing this experiment and they determined that during this reaction, dinitrogen dioxide is formed, right? So that can help us to basically come up with a mechanism for this reaction. So one proposed mechanism is that the first step in this mechanism is the reaction of two nitrogen monoxide molecules to form that species that was detected during the reaction, all right? And then the next step is where that species reacts with oxygen to form the final product, all right? So this is a very simple example of a mechanism which explains not only the overall equation, but the fact that an intermediate N2O2 was detected during the reaction. And so another thing I need to say here is that what must be true for all mechanisms is that when you add up the elementary steps, you should end up with the overall equation, right? And we can see that here. When you add up these two elementary steps, the dinitrogen dioxide is canceled out and you end up with the overall equation, all right? So that's true for any mechanisms that one could come up with in order to explain what's happening in a chemical reaction. Okay, so this is just basically representing the same reaction using models. So let me skip that. And let's talk about a term I introduced earlier without defining it, intermediates. What are the intermediates in a mechanism? Well, as you can see here, the intermediates are those species that appear in a reaction, but they do not appear in the overall equation, all right? So they appear in the mechanism, but not in the overall equation, okay? And we saw that in the case of N2O2 being the intermediate, right? Another thing about the intermediate, which is very important, is that an intermediate is always formed in an earlier step and then used up in a subsequent step, all right? So basically, the intermediate does not end up in the product at all because it's produced initially then used up afterwards, all right? So that is seen in the example that we just looked at. The intermediate in this case is the dinitrogen dioxide because it is produced in the first step and then used up in the second step, all right? Another term I need to introduce to you is this term molecularity, right? And the molecularity is a number of molecules that react in an elementary step, all right? So in the case of a unimolecular reaction or a unimolecular step, it's an elementary step with only one molecule involved. If it is a bimolecular reaction, well, the elementary step in that case would involve two molecules. Now, most, if not all, steps in any mechanism would either be unimolecular or bimolecular, right? There may be, I don't know of any, but there may be situations where you have three molecules simultaneously colliding, and that would be, at least in theory, a termolecular reaction. Now, as you can imagine, that is highly unlikely. If you think of molecules moving around randomly, right, it is highly unlikely that you have three molecules colliding at the same time, and then a reaction takes place. That is similar to three persons having, let's say, a basketball each, and those three persons throw the balls up in the air and they all collide simultaneously. That's very unlikely to happen, right? I know of no case of that happening. So as far as I'm concerned, that is virtually impossible. Okay, so basically most of the reaction or all the reactions we'll be looking at where we can talk about a mechanism will be either falling into the category of unimolecular or bimolecular. Okay, so what you'll find is that it's very easy to write down the rate laws for elementary steps, right? It's all based on whether or not the reaction is unimolecular, bimolecular, whatever. So if you have a unimolecular reaction where there's only one reactant in this elementary step, then the rate law for that reaction is simply this. Rate is equal to K times the concentration of the reactant of that step. In the case of a bimolecular reaction, there are two types. There's one type where the two molecules reacting in that step would be different, like A and B. And in that particular case, the rate law for that reaction or for that step would be rate is equal to K times the concentration of A times the concentration of B. Or another type of bimolecular reaction is where both molecules are the same, right? In that case, the rate law for that step would be rate is equal to K times the concentration of A squared, all right? So basically you can tell just by the reactant numbers in the elementary steps, you can tell what the rate law is, all right? Please note that this is true only for elementary steps. It's not true for the overall reaction, right? This is true only for the elementary steps. Okay, so just to summarize what we have covered so far, when you're writing down a plausible reaction mechanism, the sum of the elementary steps must give the overall balanced equation for the reaction. Now, another thing I need to mention here is what is called the rate determining step. I don't think I mentioned that earlier. So let me define it right here. The rate determining step of a reaction, a multi-step reaction, is the slowest step, right? And the reason why it's called a rate determining step is that the slowest step determines the overall rate of the reaction. In other words, the overall reaction rate cannot proceed faster than the rate determining step. And by the way, in some textbooks, I'm not sure about your textbook, but in some textbooks, they call this the rate limiting step. So if you see the term rate limiting, it's the same thing as rate determining, all right? Okay, so the rate determining step is very important in order for you to come to some meaningful conclusion about the mechanism and the overall kinetics of the reaction. Okay, so basically these are the steps involved in trying to determine a reaction mechanism. And a lot of chemists are basically, I don't know the term, kineticist is the term to use, but there are chemists who, that's all they do. You know, they look at reaction rates and try to determine mechanisms of reaction, which is important, especially when it comes to understanding, for example, the mechanism of drug action. All right, a lot of the principles that we're talking about here applies to that. So if you plan to do medicine or pharmacy, you know, you're going to encounter these principles and terms. If you plan to do engineering, well, I would say specifically chemical engineering, you know, these concepts are very important as well. So these are the steps involved. You do some kinetic experiments where you determine the rate of reaction, and you look at the relationship between the reaction rate and the concentrations, and based on that, you can determine the rate law. And then based on the rate law, you can formulate or postulate a reaction mechanism. Please know that the reaction mechanism is basically a theory which is supported by the data coming from the rate law that was determined, all right? Okay, so here's an example where you're given the rate law. So let's say somebody did the experiment for this reaction, and they determined that the rate is equal to the rate constant times the concentration of nitrogen dioxide squared. So it is believed that the mechanism is shown here. Step one would be two nitrogen dioxide molecules reacting to form nitrogen monoxide and nitrogen trioxide. And then the next step is where nitrogen trioxide reacts with carbon monoxide to give you NO2 and CO2. So the first question is, what is the overall equation for this reaction? What say you? They gave you the two steps. How would you determine the overall equation for the reaction? Well, remember what we said about the overall reaction as it relates to the elementary steps? What did we say? What did we say about the mechanism as it relates to the overall reaction? What must be the case? Let me give you a hint. What does it say? The sum of the elementary steps must give the overall balance equation, right? So let's go back to the question. What would be the overall balance equation? Okay, very good. So NO3 would be the intermediate because it's produced in the first step and used up in the second step. So what would be the result? What would be the resulting equation after you cancel those out? Two NO2 plus CO well, actually, no, hold on. The two NO2, one of the NO2s will cancel out. Right, so NO2 plus to give you? Exactly. So basically, those are the items that will cancel out. So basically, you're going to end up with NO2 plus NO plus CO to give you NO and CO2. All right. What is the intermediate? NO3. All right. And okay, so here's an important question, and this will show whether or not you have learned what we just talked about. What can you say about the relative steps, the relative rates of steps 1 and 2? And let me give you a hint here. The hint is right here in the rate law. Rate is equal to K times the concentration of NO2 squared. So what can you say about the relative rates of those two steps? In other words, which one would be faster or which one would be slower? Let's deal with slower. Which one would be slower? In other words, which one would be the rate determining step? Why do you say that? Which is correct, by the way, but I want to hear your reasoning. Why do you say step one? Nope. And that's a very common error that students sometimes make when they meet this for the first time. The rate determining step is not necessarily the first step. But remember what I said about the rate determining step. It is a step that determines the overall rate of the reaction. Right? Yes, sir.
Because the experimental rate is NO2 squared.
Exactly.
It would be A plus A, which matches 7.
Exactly. The rate law, the overall rate law, as you can see here, is basically rate is equal to K times the concentration of NO2 squared. Right? So according to this mechanism, if this is the mechanism that explains the reaction, then that means that the first step, which has 2 NO2 molecules, right, would be the slowest step and therefore the rate determining step, right? So basically step 1 would be the slowest step and step 2 would be faster, all right? Okay, so that's the answer right here. Okay, so let's continue about another factor that affects the rate of reaction. And again, what we're talking about here applies not only to chemistry, but for, biological systems, engineering, and all that. The presence of a catalyst. So let's talk about what a catalyst is. A catalyst is basically a substance which, when added to a reaction, it increases the reaction rate without the substance, the catalyst, being used up or consumed, all right? So basically, you add a catalyst to the reaction, and the reaction goes faster. And there are a couple of examples one can think of, which we're going to look at, but let me just mention one right now. If you take a piece of beef liver, well, firstly, if you take hydrogen peroxide and you leave it open to the atmosphere, eventually you're going to have the hydrogen peroxide reacting to form water, right? So if you leave it long enough, you'll have nothing but water left. Now you can speak, and that will take some time, maybe more than a day. If you were to basically add a piece of beef liver to it, that reaction will occur much faster. In fact, you're going to see oxygen gas leaving the mixture or leaving the solution very quickly. And the reason why is because beef liver contains an enzyme. And if you know anything about enzymes, they are also catalysts. They are biological catalysts. And basically, they speed up the reaction of the decomposition of hydrogen peroxide to form water and oxygen. Okay, so how does a catalyst work? Well, simply put, of course, it's a bit more complicated, but simply put, what the catalyst does is that it creates a new reaction pathway of lower activation energy, right? So basically, you'll have one mechanism for the reaction without the catalyst, and then when the catalyst becomes involved, the mechanism becomes different. But one thing about the mechanism is that the activation energy for the catalyzed reaction will be lower compared to the uncatalyzed reaction. We can see that in these two graphs right here. The graph on the left represents the uncatalyzed reaction. The graph on the right represents the state of affairs for a catalyzed reaction. And you'll notice that the difference between them is the value of EA changes, right? In the case of the uncatalyzed reaction, the activation energy is higher compared to that of the catalyzed reaction. So what does that mean? That means that if the activation energy is lowered for the catalyzed reaction, everything else being the same, temperature, pressure, whatever, then more molecules will have the activated, at least the value represented by the activation energy for the catalyzed reaction, and therefore more collisions, more effective collisions will occur, and therefore the reaction rate would increase, right? So adding the catalyst will affect the activation energy. It will not affect the enthalpy, right? The difference in energy between the reactants and the products will still be the same, but the peak will change or will decrease as far as the catalyzed reaction is concerned compared to the uncatalyzed reaction, right? Now, we can see as a result of that, based on the math or the equation right here, which we met earlier, the Arrhenius equation, if the activation energy is lowered, that means that the value for K would be higher, all right? And therefore the reaction rate would be faster. as a result. So as the activation energy is lower, K would increase, all right? And therefore the rate of the catalyzed reaction will be greater compared to the rate of the uncatalyzed reaction. Okay, so let's talk about the different types of catalysts that that demonstrates this sort of effect on reactions. You have what are known as, they can be put into two broad categories. You have what are known as heterogeneous catalysts, where basically the reactants and the catalysts are in different states or phases, right? And here are a couple of examples, industrial examples of heterogeneous catalysts. And then we have homogeneous catalysts, where basically the catalyst and the reactants are in the same state or phase. Usually it's liquid. And the two most common types of catalysts in this particular category are acidic ones and basic ones, all right? So let's deal with heterogeneous catalysts. We talked about, or we mentioned just now, the Haber process, which was a very important industrial process discovered by Fritz Haber, who was a Jew in Germany. He was basically, he's now considered to be the father of chemical warfare because he lent his considerable skills in chemistry to develop chemical weapons and so on. So he came up with this process because back then during World War I, in order to make explosive, they need nitrogen-based compounds. And there was a shortage. There's a long story behind it, but they had to import it, but the Allies cut off the shipping routes, so therefore Haber got to work. And he came up with this process where he converted nitrogen and hydrogen into ammonia, and then that is converted into ammonium sulfate, which can be used for explosives and can also be used for fertilizer as well. So it did have some effect on the agricultural industry as well. So basically, what happened, this is a reaction here, the reaction between nitrogen and hydrogen to form ammonia. So he developed this catalyst. He tried a variety of different things. And he also involved a process, which we're going to talk about later on, where he looked at the equilibrium balance between the reactants and products. But he came up with this combination of substances as a catalyst, right? And what happens in terms of the actual step-by-step process is that the nitrogen and hydrogen molecules will attach itself to certain regions of the catalyst, which are known as active sites. Let me write this down. So you're going to have certain active sites on the surface of the catalyst, right? And basically what will happen is that the atoms of nitrogen and hydrogen will become attached to the surface, and the result of that is breaking the bonds between the hydrogen atoms of the respective molecules, and the same will happen to the ammonia molecules. The term for this is adsorption, not absorption, but adsorption, right? Absorption is basically the process of having the atoms attracted to and clinging to the surface of the catalyst. And then what will happen is that the atoms will move along the surface and then bump into the respective other atom that it will combine with, which would be in the case of the nitrogen, it will combine with 3 hydrogen atoms. And basically, as a result of the bonds being formed between the nitrogen and hydrogen atoms, that would weaken the attractive forces between the atoms and the metal and the catalytic surface, and therefore it will release the molecules, and therefore, as a result, you have the ammonia molecules being formed, all right? So that's basically what happened in the case of the Haber process, all right? The Ostwald process for making nitric acid uses another combination of, in this case, metals, platinum and rhodium. And basically what happens is that catalyzes the reaction between oxygen and ammonia to form nitrogen monoxide and water. And then you have 2 other steps occurring, which ultimately leads to the formation of both nitrous and nitric acid. So that's just basically another example of the of heterogeneous catalysis. Okay, another example is one that is in our motor vehicles. I'm quite sure you have heard of catalytic converters. All right, so basically what happens when your gasoline is combusted in the engine is that it's not a complete combustion. I mean, one of the products will be carbon dioxide, which is a result of complete combustion, but you can also have incomplete combustion where you have carbon monoxide and other hydrocarbons that did not undergo combustion, which if allowed to escape into the atmosphere would cause a lot of issues, pollution and so on, especially since carbon monoxide is known to be toxic. So therefore, we have in our motor vehicles what are known as catalytic converters, and what they do is basically further allow for the combustion of carbon monoxide to form carbon dioxide, and the same is true for the other hydrocarbons that escape combustion in the engine of the car, and therefore you're going to end up with the products carbon dioxide and water, which are much less harmful to the environment, right? So that's the role of catalytic converters. The materials used to make them are very expensive. One is rhodium, and I forgot what I think there are two more. I don't remember exactly what. I'm sorry?
I think platinum.
You're probably right, or palladium. I don't remember, but I know one is rhodium. And as a result of that, and I haven't heard of this happening in Florida, but I remember seeing online that there was a whole lot of instances of these converters being stolen from motor cars in California, right? So basically, and it turns out that they're very easy to steal if you have the right tools, right? All you have to do is get your electric saw, whatever, and you just cut this part, and then you just take away the converter, and that's it, and then you just run off. Last I read, car manufacturers are trying to figure out how to make them more difficult to steal. I haven't heard any progress on that front yet, so that's where things are right now. Also, some other gases are converted to less harmful gases. Nitrogen monoxide and nitrogen dioxide, which is also toxic, can be converted to less harmful gases as well, using the same materials in the catalytic converter. Catalysis also is applicable when it comes to the action of enzymes. I think I mentioned enzymes as being biocatalysts. And basically, when it comes to enzymes, the first thing I need to say is that enzymes are very complex organic molecules. And the thing about enzymes is that they have within them, based on their shape, what are also known as active sites. And their shape is so unique that they can accommodate the molecular structure of a particular molecule which needs to undergo a particular reaction. So the molecule that combines with the enzyme is known as a substrate. So the substrate has to be of a particular shape in terms of its molecular structure so that it fits into the appropriate cavity of the enzyme. And then you end up with the formation of an enzyme substrate complex. And then the result would be the breaking down of the substrates into the products that you can see here. And to be perfectly honest, I don't remember exactly what this represents, but this is basically showing you the same idea, where this is your enzyme molecule. You have a cavity right here. In some textbooks, they call this the lock and key model, where the substrate is basically the key, and it goes in here and fits in here. And you'll notice when it fits in here, it alters the shape of the enzyme, and the reaction will take place, and then the products will be released from this, and the enzyme will retain its shape after that. So this is basically showing you some enzyme kinetics in terms of the different graphs showing you the energy change versus the reaction progress as the substrate is converted to a product. Now, in this case, we're talking about the uncatalyzed reaction. So as you can see, the activation energy is very large, but when you add the catalyst to it, then it goes through several steps. This is the enzyme, this is the substrate. There's a slight increase, and then you have the formation of the enzyme substrate complex. That basically has a lower energy, as you can see, compared to the separate enzyme and substrate, and then a further reaction leads to the formation of the products. Now, this particular plot is very interesting because what this shows you is the rate of the product formation as the concentration of the substrate increases. And what you'll find is as you increase the concentration of the substrate, the rate of the product formation increases until it plateaus, right? It flattens out. And the explanation for that is actually given right here. Basically, what that means that all the active sites are occupied and therefore beyond this substrate concentration. So basically, once all the active sites are occupied by the substrate, then basically adding more substrate will not increase the reaction rate. The reaction rate will simply remain at a constant value. And this is just basically showing you the equation which relates the rate to the concentration of the enzyme substrate. That would be the rate limiting step in the mechanism involved. And that's basically it for this chapter. So, based on what we have covered so far, you should now be able to, let me go back to this right here. Okay, so number 8, number 9, number 10, number 11. Oh, so I think I told you guys about the last 2 questions, right? That I added. So those are, did you guys have any issues solving these problems, or have you tried them yet? Please try them as soon as possible because I want to collect these assignments on Wednesday, all right? So I added this question, number 12 and number 13, all right? So if you have not attempted those questions before, please do so ASAP. One thing I should mention, and I just realized that I overlooked it. Let me do this quickly in the 2 minutes that we have left. So if you recall this question here, we identified the intermediate, NO3, right? Remember, the intermediate is the substance that is produced in one step and used up in another step. The catalyst would be the opposite, right? The catalyst would be used up in one step and then produced in a subsequent step. So that's a big important difference between the catalyst and the intermediate. And I mentioned that because that will be important to answering one of the questions that is in assignment number 2. All right. Okay, so that's basically it, folks. So make sure you complete the other questions. If you have any issues with any of the remaining questions, feel free to call me. I'll be in my office today from 3:30 to 7:30. If you have any questions. Unfortunately, I don't have any office hours on Tuesday. So today is the only time that I really have available before Wednesday. All right. Okay, so that's it, folks. I'll see you guys on Wednesday. Oh, by the way, let me get those who came in late. I'm sorry. Hold on. Anderson is here. Chesmore is here. Gonzalez. Jabbar. Jones is here. Papa. Simpson. And Welter.
Here.
Okay. That's it, folks.
Will you write the 2 questions that you added on the back?
I'm sorry?
Like the 2 questions that you added, do we just write the work on the back or something? We submit it?
Yeah, you could do that, yeah.
Something like that.